A very good morning and welcome back. May I request you all to switch off or put your cell phone in silent mode, please, before we begin the first lecture for today.
So good morning, everybody. Is it too loud? It's okay. Okay. Yeah. So my name is Vijay Kodiyalam. I'm a faculty member here, and the topic of my talk today is ramblings in Ramsey theory. So I should first apologize to the audience for changing the topic at the last minute. I was scheduled to speak on permutations and combinations, and I had spoken about this in another workshop for teachers, I think a year or two ago, and I saw some teachers from that workshop were still around here, so I thought I'll change the topic and speak about this. In any case, Ramsey theory is something that is even if it is not taught at school level, it's something that is very accessible. It's a branch of combinatorics, and it's certainly accessible to students in 11th and 12th standard. So this is one kind of thing, and there are many open problems in the subject which can actually be done by calculations or sufficient cleverness, you'll see. So yesterday there was a discussion on projects in the evening, which I was not there at that time, but this theory certainly has lots of problems which can be assigned and which can be worked on by students. They are difficult, but still accessible in many ways. Okay, so what I'll do is I'll begin by stating 4 problems in the theory, and then we will go through these problems one by one and try to see how to solve them and what are the methods that are common to all these problems. So by the way, Ramsey refers to a British mathematician, philosopher and economist, Frank Plumpton Ramsey, who proved one of the fundamental theorems in this subject, I think at the age of 24 or 25. He is one of those mathematicians who also died young. He died a couple of years after his proof. Okay, so I'll plunge in and begin by stating the 4 problems. So here is the first problem. So we take the numbers from 1 to 10 and arrange them in any order. So arrange 1 to 10 in any order. Then I want to assert the following. I want to assert that you can find a subsequence, that is, you can drop some of them and just take a subsequence of this sequence, which is either strictly increasing or strictly decreasing, and the subsequence of length 4. So then there always exists some subsequence of length 4 which is either increasing or decreasing. That is, no matter in what way I arrange the numbers from 1 to 10, I can always find a subsequence of length 4, at least 4, maybe you may be able to find more also, which is either increasing or decreasing. It is not possible to arrange them in such a way that no subsequence of 4 increases and no subsequence of 4 decreases. So this is the first problem. Okay, here's the next one. So the next problem concerns a collection of people, and again in this group there are 10 people. So in any group of 10 people, this coincidence of 10 is just a coincidence. In in any group of 10 people, you can always find a group of 3 which are mutual strangers, or a group of 4 which are mutual friends. So in any group of 10 people, there always is a group of 3 mutual strangers or 4 mutual friends. So let me explain this a little further. So what this means is the following. So you have 10 people, and each of these 10 people, so you pick one, and then this person will either know or not know another person. So either friend or non-friend, friend or stranger. So any pair is a friend or stranger. Now I'm saying that no matter which collection of 10 people you take, there will always be a group of 3 in those which are mutual strangers, or there will always exist a group of 4 in them which are mutual friends. That is, each is friends with all the others. So you have these 4 people, this is a friend of this, 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 and this is a friend of this. Either 4 mutual friends or 3 mutual strangers must always exist. Okay, so this is our second problem. Third problem is the following. Here we take the numbers from 1 to 9 and color them. Okay, we are going to color the numbers from 1 to 9 using 2 colors, say red and blue. So take a 2 coloring of the numbers 1 to 9. So each of these is colored either red or blue, some arbitrary 2 coloring. Then the claim is that in this there always exists an arithmetic progression of length 3 which is monochromatic, of the same color. So I color the numbers from 1 to 9 in any way, then I'm saying red or blue. Each thing gets red or blue. Then I'm saying that always there will be an arithmetic progression, all of whose elements are red or all of whose elements are blue, of length 3. Okay, this is the third problem. And finally, the last problem. Now the last problem deals with the game of tic-tac-toe. So this is a familiar game. You have a board. So little children often play this. And the players take turns. So one player has one symbol, another player has another symbol. So they take turns. So one puts, say, a circle, another puts a cross, circle, cross, circle, cross, circle, cross. And the game is supposed to end when the player with circle gets 3 circles in a row, or the player with crosses gets 3 crosses in a row, right? So this is the game of tic-tac-toe. So it has many names. And I referred to Wikipedia this morning. Apparently, some version of this game has been played since 1st century BC in ancient Rome. Okay, so this is the game of tic-tac-toe. So what about the game of tic-tac-toe? Now we are not interested in this game of tic-tac-toe. What we are interested in is in higher dimensions. So we want to play this game of tic-tac-toe not in 2 dimensions, let's say in 3 dimensions. So what would this game be in 3 dimensions? In 3 dimensions you would have a cube. So here is a 3 cross 3 cross 3 cube, right? You imagine this cube is, all these little cubies inside are empty. So this cube has, so 27 of these little little cubes. All of those things are empty at the beginning of the game, and again 2 players are playing, and one puts one symbol in one of those cubies and the other puts another symbol, and this game continues, and until, as in this game, either you must get 3 circles or 3 crosses in a row. In a row means, for example, this cube, the middle center cube and this cube would form a row, a diagonal, right? Would form the main diagonal of that cube. Or for example, this one, and this one, this would form a row. That will form one, not a main diagonal, but some diagonal on the face. So this way the game continues until somebody wins. So this is 3-dimensional tic-tac-toe. Now this last problem deals with actually not 3-dimensional tic-tac-toe, but 4-dimensional tic-tac-toe, and this is what it states. So in 2-player 4-dimensional size 3, this is size 3 tic-tac-toe. Size 3 tic-tac-toe. There is never a draw. The game cannot end in a draw. If you see in 2-dimensional tic-tac-toe, this game has ended and it's a draw. Neither the circle player managed to get 3 nor the cross player managed to get 3. And this is the reason typically why only very young children play it. They soon realize that this game is, if 2 players play perfectly, then it's always going to end in a draw, this game, this 2-dimensional tic-tac-toe. So typically only small children play this game. But in 4-dimensional tic-tac-toe, the theorem is, at least this problem, that is what it is stating, is that it never ends in a draw. One player will always win. At the end, there will always be either 3 circles in a row or 3 crosses in a row. Now, but what does 4-dimensional tic-tac-toe actually mean? How do you play such a game? So to imagine 4-dimensional tic-tac-toe, how do you go from 2 to 3? So in going from 2 to 3, so you have this 2-dimensional one, you take 3 copies of it and place one behind the other, right? So this is my first copy. If I peel off all these little cubies, the 9 little cubies in front, I'll get the 9 in the middle row. And then if I peel off all of those, I'll get 9 in the last row. So I've taken 3 copies of the 2-dimensional one and stacked them together to get the 3-dimensional one. So you can imagine doing the same thing in higher dimensions. So what must you do? To get 4-dimensional tic-tac-toe, you need to take 3 copies of this one. You need to take 3 copies of this and stack them one behind the other in your imagination in the 4th dimension. But what does that actually mean? So here is my first one. Here is my second one, and I'll draw the third one here. Each one is a copy of this, so it's divided, right? Each one is divided into the usual way. Now, in addition to the usual lines that you have in 3 dimensions, you have 4-dimensional lines. What are the 4-dimensional lines? For example, this cube, and that cube, those little ones will form one line in the 4th dimension. Or for example, this cube, the middle one of that, and that one will form a line in the 4th dimension. So it's easy to imagine what 4-dimensional tic-tac-toe means by taking 3 copies of the 3-dimensional one and using your imagination sufficiently. So this problem 4 says that if 2 players are playing 4-dimensional tic-tac-toe of size 3, that is everything is 3 by 3, then it cannot end in a draw. Like this 2-dimensional one ends in a draw, but 4-dimensional one will never end in a draw. Okay, all of these are examples of problems of Ramsey theory. So now let us see how one would go about solving these problems. I'll try to do at least 1 or 2 of them, maybe 3 if there's time. Okay, so in order to see how this is done, there is a very fundamental result which is at the base of this whole theory, and that is called the pigeonhole principle. we will see this pigeonhole principle being used in many, many ways. So here is what it states. Now it states something so obvious that one would think it's absurd that this is of any use whatsoever, but you will see. So pigeonhole principle says if n plus 1 pigeons are put into n holes, then at least one hole contains more than one pigeon. So you have n holes, say 10 holes and 11 pigeons, and you're putting these pigeons in these holes, then there's no way you can do it without one hole containing more than one, at least one hole containing more than one pigeon. That's obvious. This is it is stating something very obvious. Now it is very surprising that this obvious thing is what is at the basis of solving all of these problems. Okay, let us generalize this very slightly. So generalization. And the generalization states the following. So if nk plus 1 pigeons are put into n pigeonholes, then at least one hole more than k pigeons. That is also clear. If every pigeonhole contained k or lesser, and there are n of them, then totally you will only account for n times k number of pigeons. What would you do with that one? Right? So it's clear that if you have sufficiently large number, that is if you have nk plus 1 pigeons and you put them into n holes, then at least one of them have to contain more than k, at least k plus 1. At least one hole has to contain k plus 1 pigeons. Okay. So these two sometimes both of them are called the pigeonhole principle, and that is the basis of Ramsey theory. So let us now try and see how to apply this. Okay, so before trying to see how to apply this to these four problems, which are a little trickier, let's begin with a simpler one, which is also very beautiful, a very beautiful application due to Paul Erdős. And this application deals with the following problem. So problem. So fix a natural number n, and consider the set of natural numbers from 1 to n, 1 to 2n. So let us consider 1 to 2n. For example, n could be 10, and you are considering all the numbers from 1 to 20. In this, we are interested in some subsets. So we want a subset with the following property. So we want to take some elements of 1 to 20, put them in a subset, and this subset must have the following property. If you take any two elements of the subset, one must not divide the other, right? No two elements of the subset should be such that one divides the other, right? Following property. No two elements of the subset are such that one divides the other. So we are interested in such subsets. So one simple example in this case, if you take the numbers from 1 to 20 say, and you want such a subset, you could take all the primes from 1 to 20 and put them in a subset. For example, for instance, if n is 10, then take the primes from 1 to 20 and here is a subset of 1 to 20. No two will divide, right? They are primes, so they won't divide anything other than themselves. They won't be divisible by anything other than themselves. So this subset has 1, 2, 3, 4, 5, 6, 7, 8 elements. Right? This is a subset of 8 elements, no two of which divide, has satisfied this condition. Right? Now we can ask, is there a larger such subset? Can you find a larger subset? Now larger could have two meanings, right? If you just state it in English, then it's not very precise. Larger could have two meanings. The two meanings that it could have are, can you find a subset which contains this and which still satisfies that condition? That is one meaning of larger. Another meaning of larger is, can you find some other subset, maybe with more than 8 elements, which satisfies this condition, not related to this particular one that I have chosen. So larger has two meanings, and in what sense do I mean? I mean in terms of size. Larger subset in terms of size. Right? Certainly you cannot find a subset which contains this and which satisfies that non-divisibility condition. Because if you take a subset which is not all the primes from 1 to 20, which contains all the primes from 1 to 20, it will definitely contain some composite number, and once it contains a composite number, that composite number will be divisible by one of these, right? So certainly you cannot enlarge this, that is definite. But can you find something which has a larger number of elements? And that's easy to do. If you think about it, certainly you should not put 1 in that subset. If you put 1 in that subset, you can't put anything else. 1 divides everything. And also if you think about it, if you put 2, then you will rule out all the even numbers. So you will be ruling out large numbers, large number of numbers if you put small ones in. So that suggests that somehow you should put only large numbers inside your subset. And what can you do? You can put the largest half of this entire thing. So for example, consider the subset from 11 to 20. This is a subset which is larger in terms of size. It has 10 elements. And clearly no two divide. Any multiple will already go beyond 20. Any multiple of any of them will go beyond 20. So this subset is a subset of size n. In this case n is 10, which has this non-divisibility property. Okay, so much is easy. This you can also do for any n, of course, right? This clearly this can be done for any n. Now we pose the interesting question. The question is, can you do better than this? That is, can you find a subset which has n plus 1 elements and still is non-divisible? Right? Can you find a subset which has n plus 1 elements and is still non-divisible, satisfies this property? It's clear again that this cannot be enlarged, right? If you take any of the numbers from 1 to 10 and put it in, it's very easy to see that it will divide, all of them divide at least one of these, right? So you cannot enlarge it. But the fact that you cannot enlarge doesn't mean you cannot find a difference in subset having 11 elements. Maybe you cannot enlarge this. See, we could not enlarge this. But nevertheless, we found one with a larger number, right? This cannot be enlarged, 8 only, but still you can find a 10 element subset in some other way. Maybe you can find 11 element subset in some other way, maybe not by enlarging this, certainly not by enlarging this, but some other way can you find a subset of 11 elements. And that is the theorem of Erdős. and that states that in any n plus 1 of 1 to 2n, sum 2 must divide. That means some one of these n plus 1 must divide some other one of these n plus 1. Now, if you have not seen this before and you think about it for a while, it is really quite hard to do. At least I know I thought about this when I saw this, and I found it quite hard to imagine how one would prove such a statement. It's not at all easy to do. Although the proof actually is very easy, it just requires a nice idea. So let's do the proof of this theorem. So proof is the following. So what you do is, you take these n plus 1 elements that you have. Suppose you have found some n plus 1 elements, some n plus 1 element subset. Take all these n plus 1 elements, and any number can always be written as a power of 2 times an odd number. You take out how many ever 2's that you can, right? And then you'll be left with an odd number, right? So any number can be written as a power of 2 times an odd number. So write these n plus 1 elements, each as a power of 2 No, 2n elements are there, but we are looking for a set of n plus 1, no 2 of which divide the other. So each of these n plus 1 you write as a power of 2 times an odd number. And now let us focus our attention on the odd number part. What are the odd numbers that can occur? If you are taking numbers from 1 to 2n, and you remove all powers of 2, the only odd numbers that can occur are 1, 3, 5 up to 2n minus 1, right? The odd number part can only be 1 or 3 or 5 or 7 or 9 up to 2n minus 1. So the odd number part has to be among 1, 3, 5, 7 up to 2n minus 1. And how many are there? There are exactly n odd numbers. 1 to 2n, half of them are even, half of them are odd. So there are n possibilities for the odd number. But you have chosen n plus 1 numbers, right? You have chosen n plus 1 numbers. Each one gives you an odd number. After removing all powers of 2, each one gives you an odd number. And there are only n possible odd numbers that you can get. So that means at least 2 of these n plus 1 numbers must have the same odd number. So of these n plus 1, 2 of them must have the same odd number. Okay, let's call them P and Q, right? 2 of these, P and Q, are among the n plus 1 that you have chosen. So P is the power of 2 power something A times odd, and Q is 2 power B times odd. And these odds are the same odd, right? Now of course it's clear. Either A has to be smaller than B or B has to be smaller than A, right? Because there are 2 different numbers, right? 2 different numbers, you have factorized. The odd part is the same, so the powers of 2 must differ. If A is smaller than B, then P will divide Q, otherwise Q will divide P. So in either case, we have found any n plus 1 numbers you take, some 2 of them, one has to divide the other, and that finishes the proof of Erdős theorem. Hence, P divides Q or Q divides P. So this is a very lovely proof, uses nothing at all, only the pigeonhole principle, right? So the pigeonhole principle, which appears so trivial to state and it seems as if it's worth nothing at all, can actually help you in proving quite non-trivial facts like this one. Now let's get to that first problem that I said. Okay. So the first problem I said, if you take any 10, 1 to 10, and arrange it in any way, then there is an increasing sequence of length 4 or a decreasing subsequence of length 4. And let me state the general result. Oh, I should have said each of those 4 problems has a theorem, and all those theorems are named theorems. That is, they are named after the people who proved them first. So they are important results. This first one is called the Erdős-Zickeris theorem. And here is the statement. So in general, I'll state it in general, yeah. So the Erdős-Zickeris theorem states the following. So in any arrangement of n squared plus 1 numbers, let's say distinct numbers, there always is either an increasing subsequence of length n plus 1 or such a decreasing subsequence, again of length n plus 1. So if you take n squared plus 1 numbers, I took 1 to 10, that means n was 3 for me, so I took 1 to 10, 3 squared plus 1. But you take any n squared plus 1 numbers and just write them in any order you want, then always you can find inside that sequence, you can find a subsequence of increasing or decreasing of length n plus 1. This is what the Erdős-Zickeris theorem says. And this again is a very beautiful application of the pigeonhole principle. This time the other pigeonhole principle, the one which has m and n and k in it. So let me try to explain that proof. So proof. So let's just do I'll just explain it by means of an example. For example, suppose n is 2. Very simple case. So we have 5 numbers, n squared plus 1. 1, 2, 3, 4, 5 say. And you arrange it in some order. So I'll take some particular order. Some order, 4, 5, 2, 3, 1, right? Take the numbers 1 to 5 in some order. What the Erdős-Zickeris theorem is going to say is, then there will be a subsequence of this, which is increasing of length 3, n plus 1 is 3 in this case, or decreasing of length 3. And if you look at this, see, the increasing ones, this is increasing but only 2, and this I cannot combine with any. So you'll see increasing ones, there are only 2. Of length 2 is the maximum increasing one. But decreasing one, there is a decreasing one. For example, 4, 2, 1 or 5, 2, 1. These are decreasing of length 3. So in this case it exists, but how does that do the proof? So how we are going to go about the proof is the following. So what we will do is, for each of the n squared plus 1 numbers, consider the longest increasing subsequence starting there. Well, actually, I should have said, consider the length of the longest increasing subsequence which starts at that number. So what do I mean by that? So here are, in this example, here are my 5 numbers, and below I will write down, for each one of these 5, I will write down what is the length of the longest increasing subsequence which starts there. So if I start at 4 and I want an increasing subsequence, the only possible thing I could take is 5, and that's it. There's only one increasing subsequence which starts at 4, so this length is 2. If I start at 5 and I want an increasing subsequence, I cannot put anything, so that's it, only 5. That means length 1. If I start at 2, I can put 3 in it, and that will give me an increasing sequence of length 2, but no more, I cannot put any more, 2. For 3, again it is 1. And for 1, of course, there's nothing there, 1. So what you do is you write down these numbers, which is the length of the longest increasing subsequence which begins at that point. So how many numbers do you have now? We began with n squared plus 1, so you have now n squared plus 1 lengths. Now observe the following. If one of these lengths is n plus 1 or more, then we are finished. If it happens that there was an increasing subsequence here of length 3 starting at this point, then we are finished. We have found our increasing subsequence. So if at least one of these numbers is n plus 1 or more, then we have found an increasing subsequence of length n plus 1. Yeah.
We are not able to follow. I want you to explain the length.
Yeah, I will explain. Yeah. See, I'm looking for subsequences. Subsequence means you just drop some and consider the rest in the same order, right? That is, 4, 2, 1 is a subsequence, but 2, 4, 1 is not a subsequence here, right? So I'm considering subsequences, and I want to consider subsequences which begin with this one, right? Nothing, I'm not allowed to consider anything before. There is nothing before in this case. But for example here, I'm not allowed to consider 4 in my subsequence. I want to consider subsequences which begin here and which are increasing. So if I want to increase from this point, the only thing I can put in is 5. There is only one increasing subsequence which starts at 4, and that is 4, 5. Its length is 2. 2 elements it has, 4, 5. So I put 2 here. If I start at 5, if I start at this point, then I cannot increase further. 5 is the largest, so the longest subsequence is 1. If I start at 2, then I can put 2, 3, but I cannot take a sequence of length 3 which is increasing starting at this point. So for each one, I write down the length of the longest increasing subsequence. Now what is the theorem we are trying to prove? We are trying to prove that there is an increasing subsequence of length n plus 1 or a decreasing subsequence of length n plus 1. So I am claiming that if at least one of these numbers is n plus 1 or more, then we are finished. We have already found our subsequence. If by chance it happened that I had begun with, say, 2, 4, 5, 3, 1, then at this point the longest increasing subsequence is already 3. 2, 4, 5 is already increasing. So I found my subsequence in that case. It's the other case that we have to analyze carefully. Right? If at least one of these is n plus 1 or more, then we have found an increasing subsequence. Otherwise, and this is the interesting case, each of these numbers is one of 1, 2 up to n. All of them are less than or equal to n in the other case. If I have n plus 1 or more, finished. If not, all of them are less than or equal to n. Okay? So now I have n squared plus 1 numbers. Each one is less than or equal to n. I claim that by the generalized pigeonhole principle, some n plus 1 of these numbers, I account for n squared of them. So I still have n squared plus 1. So at least one of the numbers 1 to n must occur at least n plus 1 times. So that means some n plus 1 of these numbers that I wrote down here must be equal. In this case, some 3 must be the same. And indeed you see 1 occurs 3 times. But always I am saying some 1 will occur at least n plus 1 times, no matter how. Because n squared plus 1, if you n squared plus 1 pigeons, you are putting into n pigeonholes, at least one pigeonhole must contain n plus 1 pigeons. That's what that pigeonhole principle said. So some n plus 1 of these numbers must all be equal. So let's mark which ones are equal. So here. And then if you look at that, you see that that forms a decreasing subsequence. And that's not an accident. It is the way we have constructed it. It will always, those things, if you have n plus 1 that are equal, then they will form a decreasing subsequence. And that's clear, because the longest decreasing subsequence, increasing subsequence at this point is of length 1. The longest increasing subsequence at this point is also of length 1. If this happened to be larger than this, then this would have been at least one more than that one, right? So it must be that that one was smaller. So it keeps on decreasing. So if two things are equal, if the two of these numbers are equal, then that second one must be necessarily smaller than that first, right? So it follows. Now, these necessarily form a decreasing subsequence of length n plus 1 or more. And that finishes the proof of the Erdős-Zickeris theorem. Again, we use nothing. Nothing has been used, only the pigeonhole principle. And this is a much harder problem. Even the divisibility problem, one can, try and get an idea of how to prove this. But if you started without my explanation, if you're looking at this for the first time without my explanation, to get this theorem is really a remarkable one. The idea is very, very, very powerful and very easy, but very hard to locate how to get it. Okay, so this is the second one. Many of the theorems in Ramsey theory are of this kind. You can state it and it seems reasonable. You try examples, you will see that you will always find, for example, 1 to 10 you arrange in any way, you will always find subsequences of length 4 which are increasing or decreasing. But as to how to prove it, it's very difficult to get an idea. Okay, so yes, so let me also say that the pigeonhole principle is not just useful for proving things like this. The way I am speaking, it might appear that all problems involving the pigeonhole principle are of this kind, and you may not be interested in this kind of problem, but that's not the case. For example, it's a well-known result that if you have a prime number of the form 4n plus 1, right? Primes of the form 4n plus 1 can always be expressed as a sum of two perfect squares. And one of the proofs of this fact uses the pigeonhole principle. I won't get into that proof, but I'm just trying to illustrate the pigeonhole principle is not just applicable for problems of this particular kind I'm considering, but it's much more generally applicable. Okay, now let us consider the second problem. Now, what the second problem said was, if you have a group of 10 people, then either 3 of them are mutual strangers or 4 of them are mutual friends. So let's see how to analyze this problem and do this. Perhaps we should begin with a simpler version of this, which we will use anyway. And the simpler version is the following. This is quite a well-known problem. I'm sure many of you would have seen this before. This states the following. In any group of 6 people, there must be a group of 3 mutual friends or a group of 3 mutual strangers. Take any collection of 6 people. Some of them will know others, some of them won't know others, any collection. But no matter what collection you take, you can always find 3 people in that group, all of whom know each other. So if you take A, B and C, A knows B, A knows C, B knows C. Or all of them don't know each other, right? A doesn't know B, B doesn't know C, A doesn't know C. In any group of 6 people, you can always find some smaller group of 3 such that they all know each other or they all don't know each other. Now this, of course, these two are not, this is not the opposite of that, right? It's not if all 3 people know each other, the opposite of that is not all 3 people don't know each other, but at least one pair among them doesn't know each other. So this is not something that's, I'm not stating something very obvious here. Okay, so how do we do this problem? One way of doing this problem is to actually draw a little picture and indicate relationships between these people. So let me do that. So let me draw 6 people here as points. So here are 6 people. Now for any 2 people, either they know each other or they are strangers. Now if they are friends, I'll indicate it by a green line, and if they are strangers, I'll indicate it by a red line. For example, for this person, maybe this is a friend, maybe that is a friend, and maybe the rest he doesn't know. And I'll complete this. Any 2 should either be friends or be strangers. So maybe for this person, maybe this is a friend, this is a stranger, maybe this also is a stranger, maybe this also is a stranger, or maybe this is a friend. For the second person. Now for the third person, I've already taken care of these 2. These might be a stranger, friend, and that might be a stranger, and this might be a, let's see, friend, say. And that fourth person may be stranger, stranger. And that fifth person, let us say also stranger. So in this way, you will complete this picture, right? For any 2 people, you will draw either a red line or a green line. A red line if they don't know each other, a green line if they know each other. Then what are we saying? Then we are saying there must be a group of 3 mutual friends or a group of 3 mutual strangers. 3 mutual friends means 3 points which are all connected by green lines. 3 mutual strangers means 3 points which are all connected by red lines. So I am saying that if you complete this, no matter which way you complete, there will either be a red triangle or a green triangle. And if you see, there is indeed, if you look at these 3 people, this, this and this, they are all connected by reds in this case. But I am saying no matter how you color it, no matter how you color it, there will always be either a red triangle or a green triangle. For example, everybody might know each other, right? In which case that whole picture is full of green, there are lots of green triangles. Or nobody may know each other, they may all be mutual strangers. In which case also there is a red triangle. But no matter how you color, there will be a red or a green triangle, and that is what this thing is stating. So let us see how to prove this. Proof again is basically relies only on the pigeonhole principle. That is the fundamental principle in Ramsey theory. And it's quite easy to do. Proof. So select one of these people, right? Arbitrarily pick one of these people and divide the rest of the 5 people into 2 sets, friends and strangers. Okay? Pick one person. And divide the rest of the 5 into 2 sets, friends of this person and strangers. So what does it mean in terms of drawing lines? pick one of these points and divide all the other points into two parts depending on whether there's a green line which joins or red line which joins, whether they are friends or strangers. Now, there are 5 and you have divided it into 2 subsets, one of friends, one of strangers. So at least one of these subsets must have 3 elements. Both cannot have 2 or fewer, right? There are 5 of them. So that's the pigeonhole principle, right? Now, at least one of these sets has 3 elements or more. Okay. Now the proof doesn't depend on which one, right? Let me say there are 3 of them are friends. The same proof will also hold if 3 of them were strangers. So suppose 3 friends, at least. So your chosen person has at least 3 friends. He must have at least 3 friends or 3 strangers. Let us suppose it is friends. So your chosen person has 3 friends. Now what you can do is you can look at that chosen person's 3. So for example, if I chose this person, P, okay, then these 5 points, let's call that 1, 2, 3, 4, 5, of which who are friends? Friends of P are 1, 3 are friends, right? And 2, 4 and 5 are strangers. Right? So this is friends and strangers. Set of friends and set of strangers. At least one of these sets has 3 or more elements. In this case, the set of strangers has 3 or more elements. So let's take so not 3 friends. Let us suppose 3 strangers, as in this example. Now you look at these 3 strangers, right? Which are 2, 4 and 5. 2, 4 and 5. Among these, if all are connected by green lines, then we are finished. If these 3 were all friends, then we have found a set of 3 mutual friends. But if these 3 are not all friends, some pair among them, they are strangers. As in this case, 2 and 4 are strangers. But these 2 are already both strangers to P. So now P together with 2 and 4 will form a red triangle. So in either case, there will either be a red triangle or a green triangle. So let me not write out this proof. So ... I'll just say. So we just argued out that either 3 friends or 3 strangers must be there to this person. Let us suppose 3 strangers are there. Among these 3 strangers, if all of them are mutual friends, then we have found 3 mutual friends. If not, 2 of these are strangers and both are strangers to this one. So in that case, you have found 3 mutual strangers here. So in any case, you have found 3 mutual friends or 3 mutual strangers. Okay. So I have just 5 minutes. So let me just finish the proof of the second problem and make some remarks. So in problem 2, we are given 10 people. You have to show that there are either 3 mutual strangers or 4 mutual friends. 3 mutual strangers or 4 mutual friends. So again, you pick one person at random. So pick one. And let F be the set of friends as before. S be the set of strangers. Out of 10 people, you have picked one, so there are 9 left. So F plus S together will have 9 elements. Together they will have 9 elements. So I claim that either S must have 4 or more elements, or F must have 6 or more elements. Because suppose this S had at most 3 elements and this had at most 5 elements, that would account for only 8. What would happen to the 9th one? There are 9 people left. So one of the possibilities must happen. Either S must have 4 or more elements, or F must have 6 or more elements. Now in each case I will do the proof separately. So this is case 1 and this is case 2. In case 1, S has 4 elements, that is, this person has 4 people who are all strangers. In case 1, if the 4 elements of S it is 6 for the following. See, if I have to subtract 1. Sorry? Why it is 6? So this is what suppose both of these are false, right? Suppose both these are false. Then S will have at most 3 elements. F will have at most 5 elements. Together they will have at most 8 elements. But there are totally 9. One is I have removed there of the 9. Yeah. So there are totally 10, of which I have picked 1. So of the 9 remaining people, either the friends have to be 4 or more, or strangers have to be 6 or more. It cannot be that both of these are false. If both of these are false, S will account for at most 3 elements, F will account for at most 5 elements, together they will account for at most 8 elements. But there are 9 people. So one of these must be true. So either S must have at least 4 or F must have at least 6. Okay. Now in case 1, in the 4 elements of S, so here I have my, I'll just take a couple of minutes. So here is my person, selected person, and he has 4 strangers. S has 4 or more elements, so at least 4 are there, right, in S, in case 1. If some 2 among those are connected by a red line, then I will have found a red triangle. That means 3 mutual strangers. That's what I want to show. But if none of them are connected by a red line, they are all connected by blues, then they form 4 mutual friends themselves, which is also what I want to prove. So in case 1, either there will be 3 mutual strangers if one of these is connected by a red line, or all 4 mutual friends if all of them are connected by blue lines. In case 2, so in case 2, we have this, and there are 6 people, all of whom are friends, right, to this one. But we know that in any group of 6 people, we just proved that there are 3 mutual friends or 3 mutual strangers. If there are 3 mutual strangers in that group of 6, then we have found 3 mutual strangers. If there are a group of 3 mutual friends, then those 3 along with this will form a group of 4 mutual friends. So in all cases, there is a group of 3 mutual strangers or 4 mutual friends. Okay. The theorem of Ramsey is actually a big generalization of this thing. In the big generalization, in what sense? In what sense? One sense is you are not allowed just 2 relationships. Here you are just allowed 2 relationships among people, friends or strangers. Or you could have friends, enemies and strangers. You could have 3 relationships. Somebody could be a friend to somebody, or an enemy, or a stranger. That's 3 colors. You could use 3 colors. Then you could ask, if you have a big enough number of people and you join every pair with one of 3 colors, what are the conditions there must be in order to ensure that there is a triangle of some color, or 4 people connected, all connected by some color, or a pentagon, 5 people all connected of some color. You could ask such questions, and Ramsey's theorem says that there always is a solution without actually saying how large the number of people must be. It says there always is a solution. I don't have time to state this precisely here, so I'll stop at this point. Thank you.